Hello. Now we will study the electric field due to a uniformly charged non-conducting sphere. So this is a non-conducting sphere, solid sphere it is, and it is uniformly charged within the volume. Total charge in this sphere is given capital Q. Rho is the charge density and the R is the radius. So basically this Q and rho will be related by this formula. Q will be equals to 4 by 3 pi R cube times of rho. So volume multiplied with density will be the total charge inside this sphere. Okay. So we want to calculate the electric field due to this sphere. We'll make two cases. Like case 1 will be for the inside points. We'll be calculating the electric field for the points which are inside the sphere. So in that case, the radius R will be less than capital R and equals to. So all the points, they will be at a distance small r from the center, and the value of small r will be less than the capital R, which is the radius of this sphere. Okay. So to calculate electric field in this region, we have to draw the Gaussian surface. So we'll draw a hypothetical Gaussian surface. This is our Gaussian surface. I'm calling it G1. The radius of this Gaussian surface is small r. Okay. So there will be enough material inside this Gaussian surface because this is solid sphere. Okay, and this is the surface of that Gaussian surface. Okay. So as we already know, the electric field, since there is a spherical symmetry, because of that, anywhere in the region, there will be only one component of electric field, and that is a radial component. So whether you look inside or you look outside, there cannot be any tangential component to the electric field. So whatever electric field will be there, whether it is inside or outside, that electric field will only be along the radius, ER I am taking. Okay, so let's do the calculation. So let's first write the Gauss law. So Gauss law is E dot ds integration over to the whole surface, Gaussian surface, is equals to Q in upon epsilon naught. Now this is your Gauss law. There are two sides to this Gauss law. One is the right hand side, which is the Q in. We have to calculate the Q in, and then we have to calculate the left hand side. So let's first calculate Q in. So Q in is the charge inside the Gaussian surface. This is G1. So inside this G1, the total charge will be the charge within the volume of this G1. So we know the volumetric density, which is rho. So this Gaussian surface, the volume of this Gaussian surface, that is 4 by 3 pi small r cube. If you multiply this with the density of the volumetric charge density, you will be getting the total charge inside. Okay, but here we want to calculate, let's do this. So this will become 4 by 3 pi r cube times of rho, that is your Q in. Okay, so we got that. Now we will be calculating the E dot ds. Okay, so this E dot ds. This E dot ds will be written as E ds cos 0. You see, the any point you go for, ds will be perpendicular to the cross section area, and perpendicular to spherical cross section area is the radius direction. So the ds and the er both will be in the same direction, so angle between them will be 0. So I put it that. So this value will be E ds. Now see one thing, this er, the value of er, since there is a spherical symmetry in this body, so this whole structure is symmetric about the center of the sphere. So any two points which are at the equal distance, with respect to the center, they will be symmetric. And at all those points, magnitude of electric field will be same along with the potential. So since any point onto this Gaussian surface is at an equal distance with respect to the center, so each and every point onto this Gaussian surface will be having the same magnitude of electric field. So since the magnitude of electric field will be same, it will not depend upon the area. So I can take this electric field, magnitude of electric field outside of the area, that will, so in this case there will be only ds which will be remaining. So will have E multiplied by ds, that is the area vector, and that will give you 4 pi small r square, and this is the value of E dot ds. So now we get the value of left hand side as well as the right hand side. We have to put those values in this equation. If you put that, so from equation 1, that is Gauss law, I'm calling this equation 1. If I put it there, that will be 4 pi r square is equals to, I'll put this value, 4 by 3 pi r cube rho. So 4 pi and 4 pi gets cancelled. This r square will cancel this one. So the electric field for all inside points comes out to be, you see this, rho by 3 times of r. So electric field is a linear function of distance from the center. This is the value of electric field for all inside points in this spherical body, where the body is uniformly charged. Okay. Now you see this formula we are getting. Now let's, corresponding to this formula, we'll be calculating the case 2. Case 2, that is for outside points. So I'll be calculating the electric field for all outside points. This. And this formula, if you see, I can rewrite this formula in terms of capital Q as well. The formula for electric field in terms of capital Q, all I have to do is replace the value of rho in this equation. Okay. So if I do that, it will be 1 by 3 multiplied with 3q upon 4 pi capital R cube. There is this epsilon. Somewhere there will be epsilon also. Yeah, this epsilon. I forgot about the epsilon. Yes. 3 epsilon times of r, which will make it ER is equals to, so 3 and 3 will cancel out. So it will be 1 upon 4 pi epsilon naught q times of small r upon r cube. So this is the formula in terms of net charge. This is the formula in terms of net charge. Now the case 2, if we go for, we have to calculate for all outside points. So to calculate for all outside point, we have to draw the Gaussian surface which is outside of this sphere. This is my G2. So here there will be some area vector ds, but at the same time electric field is also in the same direction. Let's go for Gauss law. So in the Gauss law, the thing is, if you apply this for outside point, the q in is not going to change. Q in will be the capital Q. Because see, there is no other charge than this spherical body, the charge onto the spherical body. And the charge onto the spherical body is capital Q. And when we calculate the left hand side, we already did calculate the left hand side. The value of E dot ds, when we will calculate for all outside point, it will be same as the previous value, and that will be E times of 4 pi small r square. The process will remain same. So when you are calculating for outside points, you will follow the same process as this one and will be getting the same value as this one. So when we put these two values into the Gauss law, we'll be getting E into 4 pi r square is equals to capital Q upon epsilon naught. And that will make value of electric field as 1 upon 4 pi epsilon naught capital Q upon r square. So this is the electric field for all E which is greater than capital R. Okay, now you see, now we have two formulas. This is the electric field for outside point as well as the electric field for inside point is 1 upon 4 pi epsilon naught Q into R upon capital R Q. This is for all inside points. And when you go for the surface, at the surface value is Q upon capital R square. Here also it will give you the same value. So this relationship, the electric field here is a continuous function. It's not changing. Okay, now this is the electric field we are getting. This is the electric field we are getting when we are calculating it for uniformly charged non-conducting sphere. So if we draw these electric fields, so let's see the variation of electric field. Let's see the variation of electric field corresponding to this uniformly charged non-conducting sphere. Okay, so this is the surface of the sphere. So in the beginning, if you see, the electric field is proportional to R. So when you go for the R0, So for R0, meaning at the center, you have to use this formula. If you're calculating the electric field at the center, that comes out to be 0. So we'll be starting from this point. Then, after that center, when you start moving from the center, electric field is of proportional to small r. So electric field is proportional to r. This angle is not 45 actually. This angle will be some theta angle. And if you want to define the angle theta, that will be equals to 1 upon 4 pi epsilon naught q upon rq. Okay. So it will reach at some value, and that value is 1 upon 4 pi epsilon naught capital Q upon r square. And then the moment you cross the surface, this is the formula which will follow, and this formula is inversely proportional to r square. R square. So that's how the electric field will vary in the region where there is a uniformly charged non-conducting sphere. In the beginning, electric field will linearly increase and then it will start decreasing. Okay. So this is the electric field, and that's how we calculate the electric field due to the uniformly charged non-conducting sphere. Next lecture we'll see the potential due to this uniformly charged non-conducting sphere. Okay. Thank you.